today we are going to look at something which is called unsupervised quantum machine learning. So we haven't spent much time in this, and we won't actually spend much time even. So we'll just spend this today's class. But we're going to look at some of the unsupervised quantum machine learning algorithms that have been delivered. What are their advantages, disadvantages, why, uh, and in which cases can we use them? Are they just some quantum algorithms corresponding to the classical clustering or classical unsupervised algorithms, or are they really useful? And we're going to go through one paper in detail, trying to understand, what this spectrum has. But this paper is relatively old. I mean, it's a 2019 paper. It's a very good paper, so we'll go through that. There have been a couple of other papers which I'll put in the links, and I would strongly suggest you all to go through them. So why are we even looking at this field? So we spend most part of this course in looking at supervised machine learning algorithms and their quantum counterparts. And we saw that deep learning really excels at this supervised machine learning, right? And and we always kept saying this, that we want to apply quantum to problems that are hard for classical machine learning, not really to the problems which are easy. So if supervised machine learning and if deep learning is excelling at supervised machine learning problems, that means that somehow that's more or less an easier problem, right? Irrespective of the fact that it needs a humongous amount of training data or maybe large training times across parallel GPUs and so on, but it's still something that classical algorithms are being able to do conveniently, right? So we wish to apply quantum algorithms in problems which are not easy for classical ML. And one such field is unsupervised ML learning, right? Now, let's try to define the problem that we are having at hand. So here, unlike in supervised machine learning, here we'll have a data set which will be only xi. In supervised, we had xi comma yi, and of course I is the same. I runs from 1 to n. So basically, we are saying that okay, I have one data. I have n data points, and they are say all real dimensional data. Okay. Now here we have two kinds of problem. So either we are trying to find the probability of y given x, and this is called the discriminative. So this we have actually seen. This is called the discriminative unsupervised learning paradigm. So we saw this in terms of discriminative supervised learning algorithms. And this is a discriminative unsupervised algorithm wherein we try to say that, okay, what is the label and how to assign these labels? The other problem is when we are trying to find the probability of x itself, right? So this is called the generative unsupervised scheme. And in terms of generative learning, we actually went through algorithms which are generative adversarial networks and even quantum version of that, quantum GANs. And here, what is our problem? So our problem statement is, what is the distribution of these points x? Or can we generate similar points belonging to this kind of a train distribution? So if I know a train distribution, can I find out, okay, what is the train distribution? Can I generate more such points? So can I generate a set of xi's to say xm, wherein these m data points are very similar to this distribution? Okay. Now, one algorithm which is quite popular in the space of classical machine learning is called clustering, and the idea is very simple. So let me just choose a different color, or maybe let's just put in. So this is one data point, and then let's have some other data point. Another set wherein we have some other data points. Let's see. So we have several types of data sets, and here we don't know the labels, right? So one such algorithm that comes under this clustering scheme is called k-means, where what we try to find is we try to find k clusters. Okay, and can we divide this entire data set given at hand into k clusters? What we do is we typically define one point. So we'll define k different points. So we call this k centroids, and we'll see, okay, how are each of these points, where do they lie with respect to each of these centroids. So if there are n data points, we will total have a k cross n computation. Okay. Now that doesn't look too odd still, but imagine if the n is in order of millions, right? So, for example, why we were saying in the beginning of today's lecture that, for deep learning, supervised learning works very well, and deep learning algorithms kind of excel at these things. Now, if you had very large data, say millions of data, and n is in the order of millions, now what happens is your k into n, so you have a huge number of computation that starts happening, right? Now, the other thing that could be is, so if the separation was nice enough, so if you had a significant distance between these black and green, or even between these black and blue points, then you probably, so for example, this could be identified as a neat cluster, and this could be identified as a neat cluster in k-means. But if this nice separation does not exist, which we see in these two or in this two, then there might be issues. So these algorithms typically break where the density matters or there is overlap. Okay. And again, there are other constraints also, wherein typically people say that, okay, how can I identify a priori? What should be the value of k, and so on. But there are several such algorithms which give, or modifications of this algorithm, I must say, that kind of give you, okay, you can start with, say, an arbitrary number of k, and then with repeated iterations, and you can use some kind of an expectation maximization algorithms to come up with the optimal number of k or optimal number of clusters that you can create. But what happens if, this nice separation doesn't happen? So there is another algorithm which is density based cluster. So actually not just one algorithm, I should say. Um, there are a number of algorithms in terms of density-based clustering. One very popular one was DB-scan. DB-scan was, popular for a number of reasons, both for the less number of compute as well as for the ease of doing it. Now, in density-based clustering, what you'll do is you try to now follow this spectrum. So you'll say, okay, I'll not create this centroid, rather I'll see where this density is there, right? So how my points are located. And if I see that, okay, similar properties of points are not beyond this, then I can actually draw a separation here, right? So this will form as one particular cluster versus the other one will be a one particular cluster. So here also I can have something which is neatly like this, right? And the other one could start from here. So now instead of this having a centroid and computing distances, so this might be closer to this point and might be at a more distance from this point, and this point will naturally go back to this cluster if it was k-means. But in density-based clustering, you kind of solved that problem. But there are other problems that will come up. So what we have observed in classical literature is that there are a huge number of such clustering algorithms, and there is no clear winner. There are cases wherein if your data set has some kind of properties, some algorithms run better versus some other algorithms won't run better. Okay. Now, if we go back to our problem and we see that, okay, how can we do clustering using quantum, right? So let's see how can we do clustering using quantum principles. So the first way, so here we looked at, say, k-means and density-based k-means. In quantums, the first one that we'll look at is mapping to the Ising model. We'll see how we can map this particular problem of clustering. So the given is the same. You have a data set which just has xi entries. So you have these xi entries, I running from 1 to n, and you don't have any y labels, and all of these xi's are real. Now, what do? Your step one is you want to calculate the gram matrix. What is your gram matrix? Basically, you have distance between 2 points. So let's say Kij is your gram matrix, and you say this is the distance between point xi and xj. Now, of course, this is symmetric because distance function is symmetric. So you basically calculate between every 2 points. This is exactly what we were doing in the centroid calculation. The centroid, and then you are calculating the distance between any point and the centroid. Here you are saying that no, I'll first create this gram matrix wherein I have all the points and I have a distance with all the points. Now this actually helps me define a kind of a weighted graph. So you can say that I now have a weighted graph. And how does this weighted graph look like? Maybe I should create it. So let's say this is x1, x2, just arbitrarily creating something. So now this is d of x1, x2. Similarly, this is d of x2, x3, d of x2, x3, x4, x1, x4, and then again, let's also create one more, which is d of x2, x4. Now, we are now trying to model this problem into something which we call the max cut problem. Now, max cut is NP hard, right? And here what we'll try to do is we're just trying to define the cost of cut. This is so suppose we want, say we want this, and we say that this is one cluster and the rest is another cluster. So this is cluster V2, this is the rest of the is cluster V1. And how can we maximize the value of cut? And so that we can distinctly put it across two classes or say two clusters, right? So how do we write this function, this cost of cut? So say in this you have, let me write is I is belongs to R and J belongs to, say, this the second one, which is B2. Here we'll just say the distance between each point. So this distance remains the same. And let's say we call this distance one, or each entry of the gram matrix, as Wij. Okay. Now we can write our cost of this cut as 1 by 4 of, you sum all these Wij, and then you also sum for each of these ij. You have Wij and then sigma I and sigma j. Now this resembles the Ising model. And why are we doing it in this form? I'll show you why we are trying to simplify it in this form. So what MaxCut does is you want to create this maximally separated cluster here, right? And you want to do it based on the topology of graphs. So now there is no more heuristics, no more distance-based heuristics, or no more, you don't have density or any other such heuristic. You don't start with any such heuristic. You want to follow the topology of the graph and you do it. So now let's take an example. So let's say we have psi I is -1 if xi belongs to this V1 cluster, which is, or you can just say the left part, and it could be +1 if xi belongs to your V2. So if it is in the right cluster or the right one. Now, what would max cut? So max cut, if it is if it is on the same side, right? So if you take, so 2 points are on same side, then you can see that nothing changes, right? So your cost of cut remains the same. Because why does that remain the same? So maybe you can just break that also down. So sigma ij would always be +1, right? So even if it is, yeah. So even if it is, say, I mean, what could be the entries? They are in the same side, so it could always be +1, or it could be -1, -1. So it's always +1, right? So if it is +1, then the cost of cut doesn't change at all, right? Versus if you say that, okay, my 2 points are on the either side. So now you see, or should rather say on opposite side. Okay, or they are actually belonging to two different clusters. How will I find, or how will max cut help me find this? So now what my cost of this cut would become? So again, I can write this similarly, right? So sigma I, sigma j. Now this becomes -1. Why? Because you will have either -1 +1, or you will have +1 -1, right? So now this cost of cut is 1 by 4 sum of Wij plus 1 by 4 sum of wij, sigma is sigma j, right? So here this sign changes, right? Now this is what we need to maximize. Now you can do this maximization in different ways, but what we were more interested in is that okay, now we have been able to model this as, because we could model this thing as an icing model, and you can relate to these, right? So you can say that this is your constant offset and this is your coupling strength. And of course, these you can relate with your spin variables, right? So they're taking the value of -1 and +1. Now you can use any of your optimization schemes. So you can, any quantum optimization subroutine. Then this becomes your step, I think step D. Yeah. So we had the cost of cut, and your step D is any quantum optimization subroutine. And we have gone through a couple of optimization subroutines. For example, we had a detailed lecture on QAOA. You can try QAOA, or I mean, you using Qiskit or using some quantum circuits. Or if you have annealers, you can actually use annealers to do this kind of an optimization. Annealers are excellent for optimization problem. So, or you can use some other quantum optimization routines, anything that you wish to, and then you just maximize this, and you get this neat clusters identified. Okay, so this is one way, and we are going to actually look at another way, and I'll go through this paper. This was a very good paper that got published in Neurips in 2019. So it is called the Q means. It's from Arnaldus Karanidis. You guys might have come across this name. So he has been doing a lot of quantum machine learning. So there are these few very famous people you would constantly, or I would have referred several papers. For example, Maria Schul's several papers that we went through in our previous lectures, or Srinivasan Arunachalam or Anadis Kerenidis. These people have been doing a lot of work in the spectrum of quantum machine learning, right? And this paper is quite a dated paper, but we'll see the different advantages and disadvantages of this particular algorithm that he proposed, and he called it Q means. And he actually, calls it a delta Q means, and we'll go through that also in detail. So what they try to do is, can we create a robust version of K-means algorithm using some quantum principles, right? Can we leverage quantum principles and create these clusters? And this is very different from the algorithm that I just showed you, which was the Ising model mapping. But this is another way of doing it. And we'll go through the steps first, and then we'll go through the entire paper, and to understand what are the advantages and disadvantages. Here also they're doing something similar to that of a classical K-means algorithm. So we will still depend on some similarity measure, for example, the Euclidean distance between 2 points, and you will have these K cluster centers, or the K centroids, and you will iterate over and try to get better centroids after every step. Okay. And why do they call it delta? You will actually see in many places they actually refer it to delta k-means algorithm. That the reason to this is that there is a certain level of randomness and noise that is there in current quantum systems, right? So he wanted to be very well aware of that, and he sort of respects that noise component even in the order of complexity that is shown. Now, one very big advantage is that the order of complexity in comparison to classical k-means is significantly reduced. So you see that okay, it will take much lesser time as the data set increases. So with n, it becomes logarithmic. So if it is logarithmic, then even if you have a very large data set, Q means could be able to do clustering much faster than a classical K means. And we'll see in the result section that qualitatively they have a decent result as well. Now there is a catch which I should mention upfront as well. So why is this algorithm not very practically implementable? Is that they sort of have an assumption that there is a QRAM that is available. right? So which is not true. So you can't really store all of these values that you are computing and store them for each iterations and then update these values. So that would be possible had you had a QRAM. So that's the reason why this algorithm a lot of people refer to as this is a theoretical upper bound, but it is not practically implementable, and it's a probably a futuristic. I mean, there could be some implementation in future. So now we'll first go through the steps and then we'll come back to the entire algorithm. Okay. So what does it try to do? Okay, we want to find this. So we have some data set and we will find this minimum values and we'll assign these elements to the particular clusters which has the minimum values with respect to that particular centroid. And what we'll have to do for that, we'll have to do some matrix multiplication to obtain these new centroids as quantum states. And at the last step, we'll have some tomography. Okay. Now, the first step for this is that we have to estimate the square distance. Okay. Same thing that we did earlier. So you will have the distance between the data point and the centroid. So here also you're trying to say, okay, I want all the data points and all centroid. And before that, what you will do, you will put everything in superposition. So once everything is in superposition, you can compute all the distances between centroids and data points parallelly. Okay. And here they use amplitude estimation. We'll not go into that particular detail or why they require QRAM. Let's just first try to understand this particular algorithm. So the first step becomes a centroid to data point distance estimation. Okay. Now, once you have this distance estimation done and you have a tensor product for all the centroid indices, note that we are trying to do it parallelly so that in terms of time, we are not increasing our upper bound. Okay. The second thing that we do here, and this particular theorem shows, okay, why is this order of complexity or the time complexity remains order n of dn. Okay. Now, the second step we do is cluster assignments. So once I have all the distances between each of the data points, so you coherently estimate all these square distances and save them in separate registers, which they assume that the QRAM will store for them. Now you select each index j that corresponds to the closest centroid to the given data point. And then you say that, okay, I take a argmin of that particular distance. Whichever is the minimum distance, assign it to that cluster. Okay. Now here again, there is an advantage. So because square is a monotone function, they are not even doing the square root computation. They're just directly using it. And here, if you see here, how they would actually implement it is that you use an additional register. Now you initialize it to the one state, so you could just apply some not get and initialize it to one state, and then you compare. So you run a loop for the variable j, which runs from 2 to k. Okay, so you have this one, so you every time whichever value in this register j comes, so you compare that with the register 1, and whichever is small, you just swap it. Okay, so you swap with 1 if 1 was smaller, or you swap with the value in register j if that was smaller, and then you update that value in the result register. Okay, so this procedure, again, there is a cost, and throughout this paper, if you see that they will constantly try to do this space and time complexity kind of analysis, because the main advantage of Q means was that it is, polylogarithmically faster, right? So that's the reason at every step you'll find these lemmas wherein they are trying to show you this. But I will not stress upon the order of complexity. The main reason being that this is not practically implementable. Forget for a large data set, even for a small data set, because of the assumptions that it carries. Now, once we have these two steps, what we have done is we have put all our data points in superposition. We have assigned labels to all these data points. And once we have, this particular, we can't read out all these possible labels. So we need to estimate these new centroids, right? So in step 3, what we'll do is we want to now, so in the previous step, we have got these states. And what we want to do here is we want to generate this new centroid states. This new centroid state is nothing but this weighted superposition of this vectors. Okay, and you are actually you're running it for all the k centroids, and then you're checking for each of them. You're summing it across, and this is how this state looks like. So it's just a weighted superposition. Okay, and each of these weights you can actually think of that as the distance that we defined in the beginning, right? Now you measure these labeled registers. So at each point you have these labeled registers, these J points. So you measure them, and once you measure them, then after that there is only one step, which is you have to update it, and for that you have to apply vector state topography. Okay. Now you can go through the details of the paper, and I'll not go into a lot of details of this particular paper, but I'll just skim through the most important parts in order for us to understand. So there is this algorithm pseudocode here, which might be even more easier to understand if you don't want to go through the order, the time complexity, space complexity, and other details. What they are doing here is just 4 steps, right? If you remember, we went through QGANs, which had very few steps, or for quantum Boltzmann machine, which had a large number of steps. This algorithm is significantly easier to understand, wherein you just need your centroid distance estimation. You have to do the cluster assignment, the first step. And then once you have done these distance and cluster assignments, you now create the states for the new centroids and update the centroids. Okay. So this makes it quite easy. And what you do here, the step that makes it difficult to implement is after this update, they are saying that you have to now update the entire QRAM data structure. Okay, so you continue doing these 4 steps till a convergence criteria is satisfied. Now, that is where the implementation detail or the implementing this particular algorithm becomes hard. Now, for this paper, they actually do it, and we'll show you that. So they actually perform this on MNIST data. MNIST is very known data set. You have these 100 digits, and you have this 28 plus 28 digits, where almost 60,000 images of 0 to 9, and they do some PCA first. So because you can't really take 28 plus 28, it's like 784 qubits it would require if you go by, say, some basis encoding or some Z or ZZ encoding kind of schemes. So what they do is they first pre-process this data, reduce the dimensionality, just take 40 dimensions out of the 784, and then after that they will just start this delta Q means kind of an algorithm wherein they will assign 10 clusters. So because we neatly know that MNIST, because I mean, even if someone said that I'm not giving you the labels per image, but you really know that MNIST has just 10 classes, 0 to 9. And so you can have 10 centroids randomly initialized, and then you can, run your algorithm till convergence. So what they show here is this dark red line, or the solid line is basically your classical k-means, and the other dotted lines are your quantum k-means time. And if you see that they are actually showing that, okay, with with the addition of noise, so with different values of noise, we are being able to see different lines. And of course, when the noise was the minimal, um, I don't know why I'm not being able to highlight this. So if you see the very first line, which is an orange, um, to enlarge, yeah. So this first line, which is in orange, that has the minimal amount of noise here. Yeah, and that line you see is almost or quite close to the actual line, or quite close to the classical counterpart, which is the classical k-means. So by this, what they try to show is that, okay, if I do a simplistic run and I am being able to be as close as my classical counterpart. However, if if the data set was large, and here the data set is just 60,000, but had the data set been even more larger and larger, in terms of time complexity, k-means is much lesser than q-means, right? So that's what they try to show. In this particular graph, they're just focusing on accuracy to show that this algorithm is dependable and you can still run this. Now, for MNIST, you would not have seen people running clustering algorithms, because the thing is that you want to really pinpoint and say that, okay, this image contains a value 6, versus you say that, okay, all sixes are together in one cluster. right? So this particular problem of image classification, it's a supervised, or even if you treat it as unsupervised, it's a classification setting wherein you need the labels of every image. So as we said in the very beginning of the class, right? So it's a discriminative unsupervised algorithm, and not it should not be put down to a clustering one. But however, you can imagine this, that just because it has just 10 classes, right? So if I am doing a fairly good job in identifying each of these classes, now within this class, if I want to do a classification, then my task becomes very, very simple. So if k-means or something like a similar, a simple clustering algorithm could do a good job, we could have solved this problem. Now here, note this, that this line is belonging, I mean, this accuracy hovers from say 40% to 60%. It doesn't go beyond 60%. So we see that, okay, clustering is not a great tool for this kind of a problem, and probably we should just rely by the discriminative and or be it supervised on or unsupervised, but we should actually put MNIST as a classification problem. Okay. Now this is the crux of this paper, but yeah. Okay. So then we'll continue. So the second paper that I wish to cover today is an application paper. So as I mentioned, that once we have done a couple of algorithms, we'll look at some applications as well. This paper, the reason I choose this paper is not because of the application per se, but because of this particular metric that they propose in this paper. Okay, and when you see that entire fraternity in this run of finding a quantum advantage. So what are there real ways to get to a quantum advantage? There are some papers that sort of proposes these kind of, so while there are big companies looking at quantum supremacy or quantum advantage, there are researchers in academia or in industry who are actually trying to define something even more niche and saying that, okay, there might be a quantum sampling advantage, there might be a quantum generation advantage, or there might be some other quantum advantages, even not at an overall data set level, but at some other levels, we might be able to find some advantages of running these quantum algorithms. Now, that to me makes more sense in today's context, given the noisy hardware that we have or the limited number of qubits that we have, right? So now, we already have, say, IBM already has put out a 433 qubit machine. So you have 433 qubits, and now we are trying to say that you will be able to run circuits which are, say, 100 qubits wide, and say 100 circuit depth is your 100. So 100 by 100 should be very easy to run, and you should be getting quite reliable results. So the noise levels should also be pretty low for at least 100 cross 100. But even beyond that is what we want to do, right? And so if I have 433 qubits at my disposal, why do I use only these 100? Just because this 100 is very reliable, I can use that, but I can do some parallel processing for the other qubits and try out algorithms which can, similar things that distributed learning people used to do when we came up with GPUs, right? So can we apply similar lessons that we learned from distributed computing here now in these quantum computers? And how can we then, reduce effects of crosstalk and other kind of noise? That will remain a pertinent question. But today we're going to look at this particular application, and we'll see what is one such metric with which we can show some quantum advantage. Okay. So this paper, what they do is they sort of show that, okay, this is the first paper wherein they were talking about the systemic study of empirical quantum advantage in healthcare, and they have this EHR data, so they have health records, electronic health records, and with these electronic health records, they choose features and they choose training data samples, and they are now trying to build quantum models. So the main algorithm that this paper plays around with is quantum support vector machine, which we have, done in very detail in terms of this, all the proofs that are there for quantum support vector machines, which show that there is a potential that if you can define a quantum kernel which is hard enough, then and classically, and has some kind of a takes the data to a different dimension, then you can actually make it linear and make the classification problem much simpler. And we also looked at D-log kernel, right? So in a discrete logarithm problem, we saw that, okay, with optimal choice of fiducial state, you can actually make a data set which was um, highly nonlinear. You can make it very easily linearly separable. Right? So these guys are only looking at a custom kernel, and in terms of quantum support vector machine, there is no novelty. They are using ZZ feature maps and some other parameters which we'll go through. But what is most interesting is they sort of talk about a metric which comes from the manifold learning. So again, in classical machine learning, there was a I think there was there was a prominent field of study before deep learning took over, which was the manifold learning space. And a lot of people in computer vision or computer graphics typically used manifold learning for prediction of how the robots should go around by a trajectory, by a given trajectory, and all of those. So typically, computer vision and computer graphics people use these kind of algorithms in the subspace of manifold learning. There was one such metric in manifold learning, which is terrain ruggedness index, and they will actually use that in some form in this particular paper. So how they define EQA? So they say empirical quantum advantage is the incremental gain of a specific quantum approach over a classical approach for a given problem. And they will show with this kind of a matrix that, okay, there is a possibility of having a quantum advantage on a given pair of data set with some quantum features. Okay. And this particular metric is called the phase space terrain ruggedness index, PTRI, as they will constantly refer to. The main research questions of this paper is, can we enhance the prediction by applying quantum kernels? And can we systematically identify these problem instances? So what is the number of features and number of samples, or what is this combination, or what is this tuple, which can lead to some quantum advantage? Okay. Now the data set in hand, or the problem in hand, which I will say, and even in this paper you will feel that they made it look secondary, is that they were trying to predict the 6-month persistence of rheumatoid arthritis on patients with some biological therapy. So they had all these patient data, and they were trying to see that, okay, they just uh, simply oversimplify this problem to a two-class classification problem, wherein is this patient taking this persistence therapy, or this patient is not persistent towards the medication of the therapy. Okay. So ultimately they put it down to two classes, and we'll probably not focus on the actual problem, or the problem of persistence of rheumatoid arthritis per se, but we'll see, okay, how is this technique, or how is this metric useful to us, and how can we apply it across different other problems. Okay. So one thing that is important, and whatever is important, I've tried to highlight in yellow. And so they're saying, when you choose these kind of problems, if you have chosen an application area wherein you see that classical algorithms are already giving you, say, 70, 80, 90% accuracy, probably it's an easier thing and you don't even need quantum. Versus in cases where you see that these classical algorithms are struggling and are below, say, 60%, or below like a coin toss kind of 50%. There, why there could be multiple other reasons, but another level of pruning that they do is, can we see if the ratio of the number of features to the number of samples is small or large? Now, in case the ratio of these number of features, or you typically have, say, 500 features, but you just have 5 samples, right? So that in that cases, these classical machine learning algorithms, they typically fail. And can quantum machine learning benefit in this situation? So that we are trying to find these hard problems for classical machine learning, right? And this is one spectrum wherein problems are really hard. And naturally, healthcare becomes a very good healthcare, or even life science. In life science, you have a lot of these protein problems, wherein the number of features, or the feature dimension, is typically huge, very large. and the number of samples that you can generate could be much lesser than the number of features. So those are typically those hard kind of problems. So that's why they say that okay, the reason why they could identify this problem is still looks valid. Now, what do they do here? So they had over 500 features for this particular problem. Let's see where they wrote it. Okay, yeah, they had over 500 features, and maybe we'll figure out where it was written. So what they used is they used a couple of metrics for making these measurements and or for to be able to establish an empirical quantum advantage. The two metrics are F1 score and balanced accuracy. These are quite popular in machine learning. And the third one is the space terrain ruggedness index. And what does this capture? It captures the hardness of the configuration space for a given set of machine learning problems or a given set of problems, right? So what, and again, when they oversimplified the data set, and we are going to look at that, they came up with this final data, which is very a balanced data, and they removed a lot of these nuances of the data just to make the problem more attackable. And this is like more or less you can say 52% and 48%, wherein 52% people had this kind of a persistence towards medication, but versus 48% didn't. Now, you had different types of features, and what they found is that 1 to 20, so the first 20 features were typically the most important features, and they were using these different training sizes, so 50 to 600 samples. So first is 50, then 100, and for each type of feature, they were adding more and more samples and seeing, okay, what kind of setup gives me best results. They trained a large number of machine learning models, like classical machine learning models, and then they used something called SHAP on top of it. So, in classical machine learning, we typically, and you guys might have heard of this, that black box deep learning is black box, or there is a need for explainability in deep learning algorithms and so on. So, there is a lot of work in explainability for not just deep learning, but also for classical machine learning algorithms, and there are several tools that exist. For example, one of them is SHAP method, the other one is line analysis, wherein what we try to do is we try to find out explanations in terms of, okay, we'll train, so for example, in SHAP, what we do is we'll train a model with the feature and without the feature. And we'll see that, okay, what was the importance of the feature? So if the model with the feature outperformed significantly from the model which did not have that feature in its training, then we can say, yes, this particular feature is important, right? Keeping all the other parameters constant. So what they did is they had a large number of models that they trained, and then they used SHAP to find out what are those topmost features, and they had a list of features that they really found out. Now, finally, what they chose on is that, I mean, finally, what they restricted themselves is that, okay, given that the first 20 features get you around 95% of accuracy, we will just restrict to these 20 features. But again, within the 20, we'll not use all 20 together. They had a set of so four different feature values that they choose. So you can have 5 features, 10 features, 15 features, and 20 features. And for each of them, so for 5, you will have 200, 250, and 300, and so on. And that's how they create this 12-point configuration. And they'll create these models for each of these points. So with 5 features and 200 data points, 5 features, 250, 5 features, 300. So that would be 3 different models. So it's 12 different models they'll train. And each of these models training the testing accuracy would be one data point for for generating these surface plots. So now, once you have these 12-point configurations, you are now trying to get these plot these data points, and you say that, okay, in terms of accuracy, this is how the data points look like. The classical algorithms accuracy is significantly better or significantly higher with respect to the quantum algorithms, versus if you see in the F-score kind of a setup wherein you were computing precision recall F-score, so which is much more broken down analysis. So rather than looking at both the classes and just doing a weighted average or just an average or in terms of accuracy, if I say that okay, how precisely it has been able to mark class one sample in class one. So it does the detailed analysis of false positives, false negative, true positive, and true negative. There we saw that the quantum models were clearly better than these classical algorithms. However, there are these kind of cases as well, right? Wherein quantum is starting from here versus classical was here. So if you have really stopped at this particular point wherein you had say 8 features with say 200 or 220 training samples, you would actually see that okay, no, my classical algorithm is doing better. And if you go beyond, probably you will actually be able to see that no, eventually my quantum algorithms are doing better in terms of F-score. Okay. So, and okay, so one more thing to note here is for the classical SVM, they used a radial basis function, which was the RBF kernel that we also saw. And we also saw in our quantum kernels that, okay, even in quantum kernel, we can define something like an RBF or where we have a simple kind of a Gaussian function. And they used these two. So they used RBF for classical and RBF for quantum kernels. And they tried to measure the geometric difference. And just with the geometric difference, they're trying to plot this graph that you see here. So these two graphs that you see. Now in the next plot, what they are trying to show that the metric value that they are achieving using a quantum processor versus the metric value that you get in a classical SVM. So let's first go to that particular graph. So this is the geometric difference between classical and quantum kernels around this 12 configurations. And you see that it is just a ratio. So the greater the geometric difference, the more potential that you have for quantum advantage. So here, if you see, it is 8 features and 300 training samples. And versus here, you see it's something much lower, right? And here if you look at the PTRI or this particular metric, and they do a similar study here. Now, in terms of balanced accuracy, you'll see that okay, there is a part where the quantum model is doing better, and then the quantum model is doing inferior, versus the classical model is being able to do better. Again, here also you see that these two surfaces sort of have an interaction, and if I can optimally choose a trajectory, so I stay in the quantum model and then I stay in the classical model and then I stay in the quantum model and then maybe I stay for the classical model in this part, then I can actually do the best for my particular application in hand, right? So I need to know where or in which part of the cost landscape is will my classical model perform better or my quantum model perform better? And that's what they are using this particular metric, which is this PTRI. Okay, for both of them they actually show. But if you think of uh, uh, I mean, they both are similar in terms of the graphs, but of course they're slightly different in terms of the metrics. Okay. Now we'll go to okay. So in terms of quantum feature map, they just use easy feature maps. So they had equal number of qubits. So they actually ended up in using 20 qubits in their circuit. And because they had 20 qubits in their circuit, so they could not run in a lesser. So the minimum system that they had to try was the 27 qubit machine. Now again in 27 qubit machine there were this paper got released in 2021, but I know that they worked on this in 20, late 2019 and 2020. And at that time, the particular machines that they were working on were there is a significant amount of noise and things like that. Right? So they had to choose this particular cohorts that they could train on, and of course there was some amount of data imputation also done. So they first chose the data which had all the features available. So if they are looking at 20 features, can I just take in all the data points that have all the 20 features, right? So they chose that, and that led to a very, very small amount of data. And then they said that, okay, we'll take at least the first 10 features should exist, and between features 11 to 20, if there is a need, then we'll actually impute it. So how do they impute? So if there is absence or so they do mention that as well here. Um, Yeah, so they use imputation to fill in the missing data. So how do they do that? They basically take the mean of the present data. So suppose you have for some data points you don't have some particular features, then you take for the others, so you find the mean, and then around the mean with some standard deviation, you can create some sort of features there and artificially fill in. Just to have something which is some data points which have say from 1 to 20 all features clearly present, right? Now, and what were the type of features that they are looking at? So, features included several things. So, they included demographics, for example, age, weight of the patient, height of the patient, age of the patient, or the laboratory tests that you have done. So, there is a large number of, say, for example, there are a large number of blood tests. So, and each of these values, these are some real values or some floating point integers that you have for each of these levels. So, for example, how much is your hemoglobin, how much is your calcium, and all of these things, right? So now remember, these are all there could be discrete values and there could be continuous values. And for ZZ or Z, it's very easy to directly put it and load it, right? But if you remember, we also went through in our, I mean, I think. 5, 6 classes ago, we went through some other mechanisms and we saw that, okay, for discrete feature embedding, we could also use some other mechanisms. For example, if you have a particular type of feature and you want to first bin it, right? So you say that, okay, if less than 5, then it is critical, or if it is 5 to 10, and it depends on what you are dealing with. Say if you're dealing with the amount of hemoglobin present in your blood. So you can say, okay, less than 5, then 10 to, and then 5 to 13 is like normal ranges, and 13 to beyond is like more. So you can bin it to 3, right? Or you could bin it to 4. And then you have different mechanisms. For example, we went through the QRAC paper wherein we saw that, okay, if you have such a feature and if you say we can categorize it into 4 categories, then we can take this discrete feature and then we can say, okay, 0, 0, if it's less than 5, call it 0, 0. If it is 5 to 10, call it 0, 1. If it is 10 to 13, call it 1, 0. If it is, say, 10 to 15, call it 1, 0. And it's 15 up, then you call it 1, 1. Right. And now each of these you can actually map it down to a 2, 1 QRAC. So you are now needing these 2 bits, so 0, 0, or all of these were 2 bits. Now you just need 1 qubit to map it off, right? So this particular feature you can now map it off easily using this kind of an encoding scheme. So there are several encoding schemes, but for this particular paper, they only restricted themselves to ZZ encoding. And the other things are observations, prescriptions, visits. Of course, they did some NLP, because they had a lot of these physician notes. So they had to extract things from the physician notes. And they also use these national drug codes or the disease diagnosis codes that sort of gave us that uh, is this patient, when the patient first reported, were they already under some medication, or they were already in some advanced stage of that particular rheumatoid arthritis disease condition, and so on, right? And the time that they first report, so the therapy start date, that is used as an index date. And this for this study, they sort of restricted themselves to the first biological prescription that they had, and it did not be always true, but they took that as the index date. And from that time, from this initiation to discontinuation, that was the length of time that they were observing it for. Okay. And yeah, so here they actually mentioned that the number of features in this model exceeded 500. This is what I was trying to find earlier. And they say that, okay, with just the top 10 features, that accounted for 90% of the achieved accuracy. And the accuracy that they achieved was 0.64. And this is classical. Okay, so this is the classical benchmark that they previously had. And they felt that, okay, 64% is very low. So can we really do something on that? And even if you use the 11 to 28 feature, or even beyond 20, if you keep using till 500, the numbers just don't, increase drastically, right? So they're saying that, okay, with just these top 10 features, we are able to get up to 64. So these top 10 features are definitely most important. So that's what these people sort of kind of maintained. So if you look at this, that the preliminary experiments that they did with classical SBM, they took 50 to 60 training set samples, and and for from these features 1 to 20, they just kept on. And since these top 20 features were responsible for 95% of this accuracy. They restricted in the quantum experiments, they restricted it to maximum of 20 only. Okay. Now, uh, total data set was around 16,000, and they had to reduce this data set, okay, because 16,000 data set had a lot of data samples, wherein there was a lot of missing data and so on. So first they took all the data which had no missing data between at least the top 10 features. Then they took some data which had at least the 10 features plus 11 to 28 features also present, but there is some amount of missing which could be imputed. So like that, they finally reduced this data sets by these sub-selection mechanisms to just a set of 1,300 samples that they worked around with. Now, within these 1,300 samples, they were sampling a set of 200, 250, or 300 every time for different configurations, and they kept running it. Again, there are some implementation details that are given here, wherein how many random splits. So they had 200 random splits between each of these 12 coordinates. And that is interesting to know because if you have done so many experiments and even after so many random splits, your results are concise, then the results are very reliable. So if I say that, okay, I took 200 out of the 1,300 and then I have some number, then you might say that, okay, maybe these 200 were the easiest sample that was chosen. So that's the reason they make several random splits. So they make 200 random splits and they have this particular, for this entire imbalanced ratio, they ran all these experiments. Now, in terms of quantum processing, it was more than 24 hours of run that they had to do, versus in classical SBM, it was like less than an hour's job. And one disadvantage that they do mention here is because they reduced the training data and the test data, there was a reduction in the predictive accuracy as well. Okay. But they were fine with that, and they tried to establish that, okay, and as we see that they were able to establish in the landscape that there are parts of times where the classical loss or the loss function landscape is sort of flattening, or the classical algorithm is struggling or unable to learn further, the quantum algorithm could help in, right? So optimization level was set at 3. What do we mean by optimization level? So we have talked about transpilation steps. So whenever you create this particular quantum circuit that you wish to run on, say, a simulator or even on a quantum hardware, in quantum hardware it becomes more pronounced and important. So you might have used a number of gates that you felt like, but when you actually put it down to some particular machine, you can only implement the gates that are there and that are native to that machine, or that are there in that machine, right? So there is a process which is very simple, similar to classical compilation process, which we call the transpilation step. So in that transpilation step, you could have different optimization settings, and this optimization setting, this is they're directly using the optimization level 3 set by Qiskit. So the optimization levels are basically heuristics in which what you do in optimization level 1 could be, you see that, okay, what is the minimum number of gates that I need to reconstruct this particular circuit, right? So can I just reconstruct that? In optimization level 2, you can have some more sophistication. In optimization level 3, you can have more sophistication in terms of, okay, I want to minimize the number of swap gates that are used. I want to also minimize the number of noise. I want to cherry pick those particular qubits that I run on, which are, close in terms of the topology, that I can reduce number of swaps, or that have the lowest error, or that have less gate fidelity, and several other things, right? Based on all of these heuristics, we typically call them as optimization, and currently this optimization has 3 different heuristical algorithms. And it is not always very guaranteed that, okay, if you are taking an optimization level of 3, you have the best results. Although we are saying that an optimization level of 3, you have maximum number of parameters that you have considered, right, while optimization. So a lot of people you will see doing this. And yeah, the feature map thing we saw earlier, and again the number of repetitions they had set it to 2. So whatever is your answers, then they had 2 repetitions of that answers, and all the entanglement that they used was linear. Now entanglement linear means that you will have a faster runtime on the quantum processor. right? But of course, if you want to play around with this, and you can actually construct the same codes and play around with different types of parameters. If you have an entanglement which is, say, a full entanglement, or even if sometimes in case of circular entanglement, you might have a increase in, say, your accuracy or precision recall score, because this we have observed that if you have, say, full entanglement correspond, I mean, in comparison to linear entanglement, full entanglement although takes more time, gives you better results as well. Okay. And if you look at entangling capacity or some other metrics like that, then definitely you see a significant improvement in your results. And there are other implementation details, like for example, in the regularization parameter of SVM that we have already discussed in our theory class, which we call the slack variable. So they have taken different values of slack variable just to see that, okay, can we best regularize it so that we reduce the chances of overfitting or underfitting. And this is how they compute SHAP, and they get that, okay, what are the top 20 features out of the 500 feature list. And this is where, in very concisely they mention about the PTRI metric. So basically, you can consider this as a simple thing. So I can rather write it here, maybe just to show you guys, and then we'll come back to the paper. So what you're trying to do is, basically you have a data point X here, and you will have 8 of its neighbors, right? So you're trying to do a squared distance. So you will have some kind of squared distance, and then you will do a square node between your X and each of your neighbors. So it could be Xi minus 1, um, J minus 1. So if this is your Xij, then you would have your Xij, comma, yeah, Xij, comma, Xi plus 1, J plus 1, and so on, right? So you are basically trying to compute the distances from all of these points just to understand where it is. So that's exactly what they are doing here in this particular algorithm, wherein they say that, okay, if you have, say, the number of features is between 1 to n, here they consider them as 20, and you have number of samples which is, say, 1 to n, and you can have, they kept changing the number of samples. So total, what you have m into n classification problems, right? So that's the total number of problems that you intend to do. Now, what do you do in this m cross n configuration? Basically, you are saying that you are computing between this particular point ij and I minus 1, j minus 1. So the top corner point. Then you do it with I minus 1, j. So the left point from that point. So you do it with all these 8 points, and then you square root over it. So you are basically saying that, okay, for each point, and okay, one more thing that I should have mentioned. So each point is surrounded by 8 points except for the boundary points. So for boundary points, what do you do? So you say that, okay, if the boundary points, the performance result is the F score, or if it is the adjacent points are beyond the boundaries, so then you just take in 0 for those cases. Okay. And for an interior point, of course, you'll have 8 neighbors, so you can directly calculate this as these 8 things. And this you do it for that entire configuration space. So you do this for this. I write it here. Okay, so you do this for all the 12 configurations, and that's how they come up with this particular graph that we saw earlier. Yes. So this particular graph. So how will you generate these points for these particular graphs was generated using that PTRI matrix. Okay. So what is the moral from this paper, or what is the key takeaways is, first thing is, whenever we are choosing or whenever we want to do a quantum machine learning for any particular application, we should remember two points, that this application is already hard for classical machine learning algorithms. So the I mean the accuracies or whatever is your metric is below, say, 60%. So then it is something which is hard, and then probably you should think of that in the quantum lens. The second thing that you should look at is, are there, so rather than just comparing, running it on entire MNIST, for example, or running it on entire any data set, you run a classical algorithm and you run a quantum algorithm and you say that, oh no, my classical algorithm does better and my quantum algorithm is not doing better, so I don't have any quantum advantage. Can we look at, more penetrating problems in classical machine learning and say that, okay, classical machine learning is struggling. So if I have had 8 features or say 10 features or even say 12 features, classical machine learning was not being able to perform very well. As the moment I included 16 feature, 18 feature, 20 features, or even in deep learning, wherein you just throw the entire data set to it and say, I give you so many examples or so many data samples that you can learn as many features as you can. And how do you make it learn as many features as you can? You have these hidden layers, and you have you put in huge number of nodes in this hidden layer. So each node can actually learn a different feature. So there will be a large number of features. So if there's a large number of features, you see that okay, gradually they are learning better and better, right? But when there are very less number of features, these models are not being able to learn. Now, again, if there is a very large number of features, but you had very less data, then again the models will overfit. Right, so that's something that we see in deep learning. So in deep learning, we will always say that okay, you need a large amount of training data also. You just can't run with a small amount of training data. You are bound to overfit, right? So for those cases, maybe these quantum machine learning algorithms can help you, right? So we need to find the appropriate place to apply these quantum machine learning algorithms and not everywhere.